Hey guys, I have your notes pulled up for 11-2 Day 1. This is a brief introduction to vectors, and if you have taken physics, you've had some experience with vectors. I think last year in IB, which would have been the 2019-2020 school year, would have been, I think in IB, Mrs. Haley taught vectors briefly in that course, but I think that the IB curriculum is changing and she's no longer going to teach vectors in IB. So brief introduction to vectors. Suppose you have some random point on a Cartesian plane and we look at it as just an ordered pair, and we're just looking at this point right here. However, if you go from the origin and you connect the origin with that point, you travel to the point AB, now you have yourself a vector. So you've gone this far and you've gone in this direction, and this is where you ended up. You started here, you ended up here. This is the vector, usually noted with like pointy brackets, A, comma, B. This represents the change in X to get there. This represents the change in Y to get there. Oh, and a vector is a quantity with magnitude and direction. Magnitude really implies the length of the vector. The direction implies either the slope and or the direction angle of a vector. Like from an initial position of 0, what was the direction that you went? The angle of direction. So there are two vectors drawn on this graph over here. One of them's name is V, one of them's name is U. And you can see the initial point for vector V, the initial point was R, and we traveled to the point S. Initial point P traveled to the point Q. So we call this the initial point, this is the terminal point. And you can see that the vectors are equal because in each vector, to get from one point to the other, we went up 2 and right 3. So we can say that since these are equal, then the vectors are equal. Now, based on the fact that we went up 2 and right 3 to get there, this looks kind of like slope. Change in Y, change in X. Sure enough, this vector has a slope of 2 over 3, and so does this one. Change in Y, change in X. When you write a vector in component form with the pointy brackets, it's in XY order. So this is your change in X. This is your change in Y. This mimics more an ordered pair, not a fraction. So you might think, oh, okay, well, any two vectors that have the same slope have the same component form. Not true. Not true at all. Because remember, one of the things that's really important in a vector is its length. So let me show you a quick picture. I have drawn two vectors on the board. I think you can see those. I've drawn two vectors on the board. Both of them have a slope of 3 over 2. So this one, you can see I went up 3 over 2 to get from this point to this point. Slope is 3 halves. This one, likewise, has a slope of 3 over 2. Start here. 1, 2, 3, 1, 2. 2, 3, 1, 2. 1, 2, 3, 1, 2. Overall, though, I could have done 1, 2, 3, 4, 5, 6, 7, 8, 9, change in Y, over 1, 2, 3, 4, 5, 6, change in X. So the reduced slope is 3 halves, just like this one. But this one's component form is right 2 up 3. This one's component form is right 6 up 9. So just showing you that two vectors that have the same slope might not have the same component form because we usually look at slope as the reduced fraction. So this is kind of our, in component form, this is our unreduced slope of our vector. The next part in your notes tells you how to find component form. How to find component form. And it's just literally what I just said. Change in x, comma, change in y. It looks more similar to an ordered pair, not a slope fraction. Change in x, change in y. And we're making sure that we take the ending x position minus the initial x position. The magnitude of a vector is, remember this is change in x and change in y. So really it's just, the magnitude is the square root of the square of your x distance plus the square of your y distance. The square of your x distance plus the square of your y distance. This is just Pythagorean theorem. This is just finding the length of a diagonal segment using its horizontal leg measurement and its vertical leg measurement. That's all it is. It's just Pythagorean theorem. So magnitude, we're always using the positive root, so it's like absolute valued. Magnitude is just the length of the segment. That is the vector. All right. So, and this is example from pre-cal. We also took vectors out of pre-cal a couple years ago. So I'm not sure if you were in pre-cal when we did vectors or not. Component form and magnitude. So we've got the initial point is 4, -7. So you can see we're traveling this way to this terminal point. So for component form, I am going to do change in x's. So end minus beginning, change in y's. 5 minus -7. And the name of it is v. So I'll write vector v. Vector v is equal to -5, 12. That is component form for that vector. And magnitude. This is how we denote we're finding magnitude. That's how we write it. And I'm going to go positive root of my x distance and y distance. $44.25, $44.25, $169. There you go. Magnitude, component form. Moving on. Magnitude and direction angle. Okay, so if this is like all you have, this is the only information you have, let's pretend for a minute that we aren't given a graph. This is the only information we have. Let's find the magnitude first. That's pretty easy. I'm going to label what I'm doing. All right, the length of the vector is 2. The length of the vector is 2. So let's say that we don't have the graph. Let's say all we know is we have a vector with length 2. That means that somewhere on a graph, there is a segment that has a length of 2. somewhere. I don't know where it's pointing. I don't know where it starts. I don't know where it ends. I have no idea. Somewhere there's a segment with a length of 2. Now, I know that the change in direction for x is it went left 1. And I know the change in the y's is it went up radical 3. So wherever my vector was, I think from the initial point, it went left 1 and up radical 3. So it looks kind of like this on the graph. Where is it? Don't know. Really don't care. But we want the direction angle. So what we're going to do to make this easier is we're going to take this segment that has a length of 2 that's kind of slanted this way. Let's put it at the origin. Let's start it at the origin, because if we start it at the origin and we go left 1, up radical 3, start at the origin, if we go left 1, up radical 3, we can figure out what this angle is. I'm going to call this my reference angle. I can figure out what this angle is in that right triangle and thus figure out what this angle is as a direction angle. So I take this vector. We know its length is 2. I'm going to put it at the origin. I'm going to label stuff about it that I know. I'm going to use trig to find this angle. Again, I'm calling it my reference angle. And I'm going to use my reference angle to figure out theta, the direction angle. And I did that by putting it at the origin. So here I go. Let's look at this angle right here. I've got all kinds of numbers I can use because we found that the magnitude was 2. But I'll go ahead and use the information that was in the problem. So I'll go tangent for my reference angle is opposite over adjacent. And notice I didn't put negatives there because reference angles are always positive. So I'm not using the fact that that was negative. I'm trying to find this acute angle. Okay, what angle has a reference? What angle has a tangent fraction of radical 3? That would be pi over 3. So since this angle is pi over 3, we're in quadrant 2, 1 pi, theta must be 2 pi over 3. That's our direction angle. From starting position at 0, what angle was rotated so that they could put a segment of length 2 right there? Okay, so you know that this segment really could be anywhere on the graph, but we know it has the direction angle of 2 pi over 3. Okay, something I want to point out before we move on to the last problem. There are all kinds of vectors that have a magnitude of 2, not just this one. So any of those have a magnitude of 2. This one has a magnitude of 2. This one has a magnitude of 2. They don't all have a direction angle of 2 pi over 3, but they all have a magnitude of 2. Okay, moving on. Component form, all right, so we need the pointy brackets. We know the magnitude, so the length of our hypotenuse. We know the length of our segment is 3. The direction angle is 40. Now, some of you are good memorizers. I'm not. I'm terrible at memorizing. I'm pretty good at figuring things out. So if I would not have come up with this on my own. I would not have had those memorized and come up with them on my own. So I drew a segment with a 40-degree angle here and a length of 3. So the magnitude is 3, angle is 40. Component form, I need change in x, I need this distance, I need change in y, I need this distance. I need my x distance, and I need my y distance. So here's my thinking. Look at this angle. To find whichever one you find first, to find x, this is just opposite. Just kidding, it's not. This is adjacent over hypotenuse. So I can say cosine of 40 equals adjacent over hypotenuse. Cosine of 40, yep, gonna need my calculator for that one. Cosine of 40 equals adjacent over hypotenuse. Let's figure out what y is. This time it's opposite and hypotenuse. So when you take out your calculator, make sure you're in degree mode, because that's kind of weird. We are in calculus and we're using degrees, but we're not doing calculus. We're kind of doing physics. So type this into your calculator and make sure you're in degree mode. I rounded to 3. So my change in x was 2.298. And my change in y was 1.928. There we go. Component form did it. All right. Y'all have fun doing that homework.